All right, so let's go ahead and talk about truth trees, or refutation trees as we call them in this book. So refutation trees, also known as truth trees, provide an alternate decision procedure for assessing the logical properties of sentences and arguments, so validity, logical equivalence, whether a sentence is contradictory, tautologous, or contingent. And these trees are really a lot better than truth tables because they're just easier to use once you learn how to use them. They're just much quicker. And so the first thing to understand is that really the basic idea behind refutation trees is really the same as what we were talking about in the last lecture. So let's just really quickly review that again. So remember that when we use a truth table, we can do it for a lot of different things, and one of them is to determine whether an argument like this one is valid. We'll just use the simple example. If P then R, not P, therefore not R. So how do we do this? Well, remember that you don't have to fill out the whole truth table, which is nice. You can if you want to, but you can really shorten the task by realizing this one thing, which has been hard for people initially to get their mind around, but hopefully it's starting to come more naturally now. The only way for an argument to be invalid is for it to be possible for the premises to be true and the conclusion false. And that's just because, of course, a valid argument is one where that's impossible. So what this means is you really only need to look at the lines of the table that could produce that result, true premises and a false conclusion. And so that's how you just start. I've made this abbreviated on the hope that we could just get this done in one line, which we can. So what you do is you assign false, to the conclusion, false to the conclusion, and true to the two premises. And then all you do is backfill. Notice we didn't put any assignments under P or R over here as we would normally do. You just go ahead and backfill the truth values as is required by this particular assignment. So of course you'll notice that because not P and not R, since not P is true, P has to be false, and since not R is false, then P has to be true. And then you just check and see, well, we're done at this point, but we need to check and say, is this okay? If you have a conditional, is it possible for the conditional to be true under this assignment? And the answer is yes. So as a result, we've supplied a counterexample, which means that this argument is in fact invalid. Now, also remember that how this works for a valid argument. So if you look at something like if P then R, not R, then not P, which is a valid argument, you already probably recognize it as such. Again, you just assign true to the premises and false to the conclusion, backfill again, and then we get something very different, right? Because not R requires us to say that, not R being T requires us to say that R is F, not P being F requires us to say that P is true, so true here and false here, and then we check and say, oh, is that okay? And we can see that it's not okay, because when we have a true premise, a true antecedent and a false consequent in a conditional, that has to be false, right? So this is not okay, and therefore this is a contradictory assignment of values, and so as a result, we would conclude that this is a valid argument. Okay, so that's all just review. Recall that, by the way, that is in the yellow box here, that if there had been more than one way for the conclusion to be false, we'd have to show that a contradiction arises in every case. Now, in this case, there's only one way for not P to be false. But if it had been, say, a conjunction, there's three ways for a conjunction to be false, and we would have had to look at all three ways. Okay? Okay, so what's the idea behind refutation trees? So the basic idea is just what we've been employing above. The idea is that in a valid argument, if you assume that the premises are true and the conclusion's false, it's going to produce contradictions in all possible interpretations of this assignment. And so we develop a quick method of representing when we've got contradictions in all possible assignments, or whether there is an assignment that doesn't produce a contradiction. Okay, so refutation trees are called trees because they look like trees. They look like upside down trees, actually, and they have branches. Now, when we talk about branches, we talk about the nodes of branches, and that's where the branching occurs. Branching occurs at a node, right? So in a refutation tree, the nodes are constituted by propositions, by formulas and subformulas. Okay, so these trees take advantage of some interesting facts about propositions and propositional logic. There's several of them. The first important one is this, and absolutely any proposition in propositional logic can be represented or captured by either a disjunction or a conjunction. Another way of saying that is that any proposition in propositional logic is logically equivalent to a conjunction or a disjunction with or without the use of the negation sign. The second fact is this. So I'm just telling you that. We're going to show how that's the case later. The second fact is that conjunctions and disjunctions can be represented by branches on a tree. So let's go ahead and see how that second fact works first. So first, let's see what we mean when we say that conjunctions and disjunctions can be represented by branches on a tree. Okay, well, this is how you represent a conjunction using a tree. A and B. Being a little bit informal here, I'm not using the meta language, so I'm not using psi and phi the way the book ordinarily would, or even italicizing them. So this is just an example. A and B gets represented like that. This is how you represent A and B by the tree method. So you decompose A and B by putting A and B on a line together. Now, we don't draw the line in this system. We don't draw that line, but we could if we wanted to. Don't do it, but if there are systems that would actually draw that line. We just don't do it in this particular system. But that would be what the branch would look like. It's a straight branch. Basically, it's not branching. It's just a straight line. Okay, so the branch really represents, it tells us in a really physical way, right, that for A and B to both be true, the branch has to run through both A and B. This is how you represent a disjunction using a tree. So what this is telling us, again, in a very graphic way, is that for A or B to be true, you can go through either one. So ORs are branches. OR is where the real branching occurs. If A or B is true, then that could be because A is true or because B is true. Either one of these branches can be traveled down, and you'd still have the original proposition being true. So consider a formula like this, a bigger formula. The the way this is going to branch is you're going to say, first of all, you're going to see that, okay, the or here is the main operator, and we always operate on the main operator of the formula above. So the main operator is or, so this is a formula that's going to branch. It's going to branch to A and B on the one hand and C and B on the other hand. And then we can also work on A and B and C and B. So A and B and C and B are going to branch or decompose into A, B, C, B. And that's because this is, we've got here is the conjunction, right? And so we've already learned with the conjunction, we get this relationship, although we don't draw that line. Okay? So that's the, with some formalization that occurs later, that's basically the way you would construct a tree for this particular proposition. Now, if you consider a formula like this, where we've switched the conjunction and the disjunction, so now the conjunction is the main operator, what you're going to get instead is this, right? So A or B, I've left off the brackets, A or B and C or B, right, on a line. Okay, and in the next step, we would be decomposing or working on A or B or C or B. Now, what's interesting here is that if, for example, we work on A or B first, which would be a natural thing to do, this check that I'm making right now is something we actually do use later. It's actually required. We would branch A or B underneath, right underneath these two, right? So A or B. And this check actually shows that we have already operated on this proposition. And then in the next instance, we would branch C or B. And we'd have to branch C or B under both of them. So we got A going to C or B and B going to C or B as well. Now, why is that? Well, it's because this tree is now giving rise to multiple interpretations, and they all have to be developed, right? So a basic rule, which again we'll just formalize, present in the next lecture, is that whenever you decompose a particular formula using the rules, the branching rules associated with it, you always write it under all the formulas that are under that formula. So when you're operating on C or B, you recall we had already done A or B, when you're operating on C or B, you are done with C or B only after you've written it under both A and B. All right, so that's the intuitive basis of how trees work. And then in the next lecture, we're going to formalize this a little bit and adopt some rules for doing this in a absolutely well-defined manner.